Hello and welcome. Today, we're going to be exploring the world of quantum and classical mechanics and why they're completely incompatible. Today is going to be a podcast-style video where I'm going to be talking with little to no visuals. Enjoy! In 1900, Max Planck, a renowned German physicist, proposed the idea of quanta, or tiny discrete packets of energy, which so far cannot be divided into smaller particles. In other words, quanta are the smallest units of observation in the universe. This fundamental concept governs all of quantum mechanics, a branch of quantum physics which itself is branched from physics. Thanks to Planck, we now know quanta is an inalienable concept of physics. Computer chips, quantum computing, and further studies in subatomic chemistry require the basic understanding of quanta, along with the numerous complex theories of quantum mechanics. However, in the world of physics, quantum mechanics contradicts and fails to align with the ideas of another crucial sector of modern physics, classical mechanics. Within this branch of physics lies general relativity, a theory of gravitation developed by Albert Einstein. Prior to this theory, physicists of the time assumed that gravity is an invisible force that attracts two objects of mass, an understanding proposed by Isaac Newton. Meanwhile, Einstein suggested that gravity wasn't an invisible force, rather a bend in space-time. Never before did physicists unite the worlds of space and time, the fourth dimension. This creates a new continuous plane of existence, or fabric, simply called space-time. This proves the 4D world exists: length, width, height, and time. Even so, we only experience the universe in 3 spatial dimensions, excluding time. Although we are actively moving through time, it is physically impossible to access what came before or what comes after the present. This means the present is constantly changing and is different for everyone, due to our displacement in space-time, which leads to an individualized, biased perspective. The concept of space-time is relatively simple to comprehend. Imagine an empty vacuum. The vacuum itself, or sheer space, is made of stuff. This stuff is the inherent emptiness of the vacuum. The presence of this nothingness is still something that is always existing. This something, or stuff, is a fabric that weaves into the universe. But this fabric is not a thin cloth that wraps around the borders of the universe. Rather, it is the invisible stuff that allows the universe to be empty. Imagine the universe is a balloon and the air inside is entirely fabric. However, the key difference is we cannot feel this fabric, but it's definitely there. Now that we have established the space in space-time, it's time to tackle how time can intervene in this pure matter concept. Einstein believes as an object moves, its speed can cause time to appear distorted. For example, let's set up 2 mirrors adjacent to one another. Between those mirrors, a light beam is bouncing back and forth. This setup is in a train traveling at 90% of the speed of light. Object 1 is a resting observer and is watching the train move as it carries the light beam while it's continuously bouncing between the adjacent mirrors. For simplicity's sake, let's say the train is traveling in a circle around Object 1. Since Object 1 is not moving or stationary, it will see the light beam's path as a diagonal line. This is because, as the light beam travels between the mirrors, the train is also moving the entire setup forward. Hence, the light is covering more distance. However, the light beam cannot travel faster than its assigned constant. This begs the question, how can the light beam travel more distance in the same amount of time? The only explanation for this strange truth is that time is moving slower for the light beam. The scientific term for this concept is time dilation. This is why Object 1 sees the light beam travel more distance at the same speed in the same amount of time. If you are still confused, no worries. Although these concepts are crucial to all branches of physics, the differences and incompatibilities between quantum and classical physics are relatively comprehensible. The biggest contradiction between these unique mechanics of physics are two concepts: analog and discrete. As explained before, Einstein's theory of general relativity is considered the analogous understanding of physics, where energy, matter, and space are constantly under continuous change. In other words, when a car accelerates, the graph forms a smooth, upward curving line, assuming time is plotted on the x-axis. However, there are numerous ways to graph information. Let's say we use a bar graph to represent the acceleration of the car. This would mean each individual bar tells us the car's exact speed at a single point in time. For example, at 0 seconds, the car's speed is 0 miles per hour. However, at 1 second, the car's speed is 1 mile per hour. But what if we want to know how fast the car was going at 0.5 seconds? Then we need a new bar to represent that exact moment in time. But what if we want to know the speed at 0.33330422 seconds? This paradox is inherently infinite. For every new request, we need a new bar added. It is nearly impossible for a bar graph to account for every single moment in time. This example proves a bar graph can be considered as a basic yet fundamental explanation of quantum behavior. In quantum mechanics, similar to individual bars in a bar graph, physical properties like energy exist in discrete units called quanta, rather than a smooth continuum. On a side note, the biggest misconception regarding quanta is quanta and quarks are synonymous terms. This is absolutely not the case. Quanta, or quantum particles, are a fundamental classification in physics. These tiny particles are invisible blocks that make up the entire universe. Quarks are not the only universal building blocks, or elementary particles. According to the Standard Model, there are 17 different elementary particles. Some possess mass, while others are just massless force carriers, like photons, which carry light. Another indisputable difference between classical and quantum mechanics is scalability. Classical mechanics describes how objects move at everyday scales, such as falling apples or orbiting planets. On the other hand, quantum mechanics describes the behavior and interactions between small, indivisible particles. The physical laws of the quantum realm do not necessarily apply to the same rules which govern the classical world. This inherent difference suggests classical mechanics as an estimation of everyday movement, whereas quantum mechanics allows us to observe and calculate everything at the tiniest possible state. Interestingly, scientists are actively trying to unite classical and quantum mechanics. This effort is part of the quantum field theory, a framework that describes how quantum particles like electrons and photons interact through fields which also incorporate aspects of relativity. Essentially, it's an attempt to bridge the gap between the smooth, continuous world of general relativity and the discrete quantized world of quantum mechanics. While quantum field theory has been incredibly successful in explaining many phenomena, physicists are still searching for a complete theory of everything, a single framework that fully unites both classical and quantum physics. That's it for today's video. Thank you so much for listening and have a wonderful day.